Okay, so this week, today, we will continue our discussion about equilibrium of rigid body, but now we will discuss on higher dimensions, so in 3 dimension. So in this case, that we need to add also the equilibrium at the other axis, and especially for translational equilibrium. So in addition to sigma fx equal to 0 and sigma fy equal to 0, we have also to consider that sigma fz should also be equal to 0. Then in terms of rotational equilibrium, then we have also to consider the sigma moment uh, on x-axis also should be equal to 0. The sigma moment component in the y-axis also should be equal to 0, and sigma mz also should be also equal to 0. Similar to two-dimensional analysis, the procedure first is whenever you face a biomechanical problem, a statics problem, equilibrium problem, you need to draw the free body diagram. Okay, so first draw the boundary of the chosen section and detach or separate it from all other bodies. And when you find a body with mass, then you have to consider its weight, which is equal to the mass times the gravity acceleration. And this weight acts at the center of gravity of the body in the vertically downward direction. This is assuming that the body has a uniform distribution of weight. In later chapter, we will also learn when we have non-uniform distribution, in which case then we will need first to determine the center of gravity. After putting the weight for a body with a mass, then we input all the external forces acting on the body from the surrounding. If the system involves cables, then the force in that cable must act outwards of the body. That is, the cable must be in tension, must be pulling. Put the reaction where the body touches or connected to a different rigid body. So whenever there is connection of that subsection or that section or that sub body to the other body, then there should be a reaction force. Otherwise, it is not in equilibrium. Equilibrium is achieved or is obtained because there are reaction forces. Then also, since we are speaking about rigid bodies where there is moment, it means then do not forget the dimension. To put also the dimension in the free body diagram. This is important. Do not forget the dimension, the size, so that then we can calculate the moment. So speaking about reaction forces at the point or at the surface where two sections or two bodies are touching to each other. So there are several types of them. So first is when you have a single reaction force with a known line of action involving one unknown. So this is when the force, the reaction force must be perpendicular to the surface and must point towards the free body. So here, for example, we have we have this first uh, body in touching this surface with the interface as a ball. So we know that this what do you call it, a beam or a plank, whatever, can move in this direction, can also move in this direction, okay, but cannot move into the surface because there is this floor below it. So it means there should be a reaction force below towards that body, yeah, and then that's why we draw it as this one, a single reaction force pointing towards that body from the surface of interaction. Similarly, also with this second type of interaction, you don't have a ball, but you have frictionless surface. So it means this body can slide slide through this direction, but it cannot slide into the surface, right? Because there is a reaction force from the surface towards vertically upward, towards the dead body, which hold that body so that it cannot go down into the surface. Okay, let's continue. Now, when that body is connected to a roller, which can only slide in one single direction, so then it means the interaction between that body and the surface contains two reaction forces. So one is perpendicular to the surface, is pointing towards the free body, yeah, because that body cannot go into the surface. And secondly, the other one is 90 degrees to a tangent to the surface that can be directed either way, but not both, preventing translation in the two direction. So, for example, in this first case, yeah, we know that this body, the whole body, cannot go into the surface. So there should be a reaction force from the surface towards that roller. This, however, can slide into the direction of that roller, yeah, into the direction of the wheel of the roller. This one, it can slide through. However, it cannot slide in this. Let's say if this is x, yeah, this is x, upward is y, this is z direction. It cannot slide also in the x direction. So it means there is a reaction force in the x direction. You can draw to the left or to the right, depends, yeah, up to you. Later, when during the calculation we find the value to be negative, then we know that it is supposed to be in the reverse direction. So here we draw it as Fy and Fx. This is the reaction component, reaction force component. Yeah. Similar to this first case, in the second case, it is a roller or a wheel in a rail. So here we know that this one cannot move in the x direction. So there should be a reaction force, yeah, in the x direction. There's also reaction force in the z direction because it cannot move vertically downward or downward towards the surface. But it can roll easily, freely in the z direction here. It can roll freely in this direction. Okay. Then when it is completely pinned, let's say like that, yeah, in a rough surface. So it means it cannot slide in all the three direction, in all the three translational direction. Like that, it cannot slide in the x direction, in the y direction also. It is withhold, yeah, withheld by the surface. So there is a reaction force from the surface. In the z direction also because it is rough, then it cannot move in the z direction. So it means there are three reaction forces here. Fx, here Fy, and here this is Fz. Okay. Similarly, also when the interaction is like a ball inside a socket, like in the joystick, you know, if you play with joystick for game, I'm not sure in today's game how we play it. So, but in previous time we often use joystick, yeah, to play game. So that stick we cannot slide translationally in this axis, nor we cannot slide it either. We cannot slide it either in this axis, and we cannot also slide it in the vertical direction. So it means then there are three reaction forces in the x-axis, the y-axis, and the z-axis as well. Yeah, as shown in this graph. Three force component, three reaction force component. Okay. Now we may also have four reaction, which involve three translational force reaction force and one reaction moment. So it means we have four unknown. So for example, in the previous case, it can still rotate, right, about that interaction point. This joystick, for example, can still rotate it can still move rotationally in about x. This is x-axis, yeah. For example, this is y, this is z. It can still rotate about x-axis. It can still also rotate about the y-axis here. right? Easily around this point. It can also rotate about the z-axis. So there are no reaction moment at the interaction between that stick with the surface. Yeah. On the other hand, if, for example, we have the interaction like this, yeah, this is a universal joint. So you see here that this one, between them, between the two components of the joint, it cannot move in this direction. Cannot, right? It cannot move in this direction. So it cannot move either in the y-axis in this direction. No, it cannot move. In the z-axis also, it cannot move, right? Because it is being completely fixed by this joint. And however, it can move still in this axis. It can still rotate in this axis. So about, this is z, this is x, and this is y. So it can still move about the z-axis. It can still also rotate about the y-axis here. Okay, this part, this part can still move about the y-axis. However, it cannot rotate about the x-axis. This is not possible, yeah, because they are fixed in this joint. So it means there is another reaction component, which is the reaction moment about the x-axis. This one, mx. So there are four unknown, the four reaction forces and moment. Reaction force at the x-axis, fx, reaction force at the y-axis, fy, and reaction force at the z-axis, fz, plus one single reaction moment about axis x. Yeah. So the first component prevent translation in the three direction. The universal joint uh, is here designed to allow rotation only about two axes, but not or about the other axis. Okay. Then we can also have six unknown. When, for example, here a fixed support, when a pillar is completely planted inside the surface. Let's say, for example, in the building, usually you have pillar at the foundation, right? Completely fixed in the ground, inside the earth. So it means that that pillar cannot move translationally in the x-axis, nor can it move in the y-axis, nor can it move in the z-axis. It cannot also rotate about the x-axis. It cannot rotate in about the y-axis. Yeah, in this axis, it cannot rotate, nor can it move in the z-axis. So it means it has three reaction forces and three reaction moments: fx, xy, fz, and mx, my, and fz. Then you can also have two force components and two couples involving two or four unknowns. This is mainly designed to prevent translation into direction. So here it can still, this is a bearing. It can still slide in the x-axis, so it doesn't have any reaction force at the x-axis, but it cannot move in the z-axis, nor can it move in the y-axis. It cannot rotate also about the y-axis. It cannot rotate about the z-axis, but it can still rotate about the x-axis, right? It can still rotate about x-axis here. It can also still slide in the x-axis direction. So it means it has four reaction forces and moments. So a reaction force at the y and z, and two reaction moments at y axis and z axis, my and mz. Okay, so now here we can also have five unknowns when that support or interaction can only rotate at one, or can only rotate about a single axis. It cannot translate in all the three axes. It cannot also rotate about two of the axes. So this is, for example, usually hinges. hinge and bearing, supporting axial truss, and pin and bracket. So for example, in this pin and bracket, it can still only rotate in this axis, right? So in about x-axis, but about the y-axis is here. It cannot rotate at all. About the z-axis, cannot rotate at all in this part. It can only rotate at the direction that is designed or proposed by this pin and bracket design. It cannot translate in any of the x, y, and z axis at all because it is completely pinned. So here we have 5 reaction forces and moments: Fx, Fy, Fz, and My and Mz here. Yeah, My and Mz. It does not have Mx reaction force because it can still freely rotate about the x-axis. So similar with this one, hinge can only rotate in a single axis. It cannot rotate in this direction, no. It cannot rotate also in this direction, in about the y-axis, and it cannot translate at all in any direction. Yeah. Similarly, this one, it can only rotate in this direction, in the about point x-axis, but cannot rotate in the other two axes, about the other two axes, and cannot translate at all. Okay, so these are the interaction between different components or structure connections, yeah, in the 3 dimension. So when you are exposed with any problem of rigid bodies in 3 dimension, well, basically in any biomechanics problem or statics problem, first, most importantly, you have to draw the free body diagram. Knowledge on determination of force component, reaction and cross and dot products for taking moments are essential. So be careful. With 2 dimension, it is enough to know moment equals to Fd. But with moment in 3 dimension, we know moment about a point, okay, which is acquired by cross product. We also have moment about an axis, which is acquired using dot product. So please review again the slides on those concepts, yeah, cross and dot products for taking moments about a point and about an axis respectively. So there are 6 equations, yeah, on sigma fx equals 0, sigma fy equals 0, sigma fz equals 0, then sigma mx equals 0, sigma my equals 0, sigma mz equals 0. So it can be up to 6 unknown. There can be up to 6 unknown. If you have a problem with more unknown, then you have to use the equation of moment about an axis. For example here, so we have a beam here, and the interaction is a socket. So it means how many reaction forces or moment here? If you look at this, so it means that's it. So for now, disregard the rope and the pulley. No pulley, the rope here. So how many reaction force at O or moment? So by looking at this interaction, you should be able to imagine where can it move, where it can move, where it can rotate about. Can it still rotate or not, this structure?
No.
About point O. Yes, it can, because it is a socket. Yeah, it can still rotate about the z-axis. It can still rotate about the x-axis, right? Because this is a socket, so like a joystick, as I mentioned. So it can still freely rotate. It
But
can
there are
also,
ropes di situ ya, Pak.
kenapa? Yes?
Kan ada ropes-nya, Pak. Nggak ketarik gitu, Pak.
Yeah, no,
Atau
I said disregarding the
oh,
rope first. Yeah,
oke
just
oke.
looking at the connection of O. Yes, it can still also rotate about the y-axis, right? So basically at O, there are no reaction moments here. What are there is what? Reaction forces. right? There is a OZ here, there is OX, and there is OY, reaction forces. So because it is fixed there, it cannot move. The bar cannot move translationally in along the x-axis. It cannot move translationally along the y-axis. It cannot move translationally along the z-axis. But it can still rotate about point O, about the x-axis, about the y-axis, about the z-axis. Okay. Then there is this tension rope fixed at point A into the wall at C and D. So this will provide the necessary moment to hold that bar, right? So that then it will stay in its position. So you are asked then to determine the tension in cables AC and AD and the reaction at the ball and socket joint at O. And when there is also here the vertically downward external force at 140 Newton at B. Okay, so from here we draw the free body diagram. Be careful in since it is also about moment, you have to state the dimension as well. Okay, so based on the previous picture, you can draw here between the y-axis to C is 0.6, between the C and the z-axis it is 0.7 meter. Okay, it is located at the YZ plane, the point C, so it does not have any distance to in the x-axis. D also similarly is 0.3 meter from Y axis or the Z coordinate, and 0.2 meter from the Z axis or the Y coordinate. The point A is located at the X axis, so it doesn't have any Y and Z coordinate component, but it only has this 0.6 meter X coordinate component. The force at B only has the location is 1 meter from the origin position O, and it is directed vertically downward, so it only has Y component or J force component, yeah, along the J unit vector. Then we have TAC and TAD, the one that is the questions. So you have to draw this correctly, otherwise then you cannot solve mathematically or analytically. After this, find the force first. It's only vertically downward, so we know that it is 840 Newton and negative J, right? Negative 840 Newton J. And the tension at cable AC, first you find the unit vector. Yeah, the dx is minus 0.6 meter because it is from A to C. Yeah, 0.6, so it is towards negative direction of x. That's why the dx is negative 0.6. The dy it is going upward, so 0.7 meter of distance. So dy is 0.7 meter, and the dz is 0.6 meter in the positive z direction. So then you can use Pythagoras theorem to calculate d, and you obtain 1.1 meter. So from there, you can express the x component as the AC. So lambda x is minus 0.6 divided by 1.1. Lambda y is 0.7 divided by 1.1. Lambda z is 0.6 divided by 1.1. So each of this is multiplied to the magnitude of the AC here. So if we express the AC in vector rotation, so TAC equals to negative 0.545 TAC. And Newton I plus 0.636 TAC Newton J plus 0.545 TAC Newton K. Similarly, we can do the same procedure with TAD, calculating first the lambda x, lambda y, and lambda z. AD here, the x component is towards the minus x axis, so minus 0.6 meter here. The dy component is towards positive y axis, 0.2 meter. Yeah, and the dz component is towards the negative x axis by minus 0.3 meter. Okay, so from here we can calculate the d from the square root of the sum of the square of dx, dy, and dz. We obtain 0.7 meter. Then we can express the AD in terms of its x and y z component multiplied by the unit force factor, yeah, I, J, and K, unit factor at x, y, z axis. That is I, J, and K. Like this. Now, similarly, the reaction force at O we can express as O equal OX Newton I. Yeah, remember that if you use handwriting, you have to put cap, okay, in the unit factor. Don't forget. OX Newton I plus OX Newton J plus OZ Newton K. Okay. From here, then, using equilibrium equation, you can express in the x-axis, yeah, in the x-axis, looking from here, sigma fx equal to 0. So OX plus TAC x plus TAD x should be equal to 0. So minus 0.515 TAC here, minus 0.857 TAD plus OX equals 0. And similarly in the y and z axis. Here we have how many unknowns? We have TAC, TAD, then OX, OY, and OZ. So we have 5 unknown. However, we only have how many? 3 equations. So from linear algebra perspective, this is not enough to solve the problem. So here we solve first for the component of moment. We have to use another equation. We use sigma moment about point O, okay, caused by all these 3 forces, yeah, the negative 840 Newton J, then the TAC and TAD. Okay, the moment about point O caused by the vertically downward external force can be calculated using ROB. Remember the definition of moment in 3 dimension, R cross F. So ROB cross negative 840 Newton J. Okay, why ROB? Because this vertically downward force happens at point B. This is so we have to express this as ROB, yeah, which is 1 meter I, right? Because it is in the positive x direction. Then plus ROA times TAC, cross product TAC. Yeah, this is TAC is here, and the beginning point of TAC is located at point A. So you can use ROA cross product TAC, or you can also use ROC cross product TAC. But it is simpler if you use if you use ROA, yeah, because it is straight 0.6 meter high, right? Similarly with TAD also, then you can use plus 3 ROA cross product TAD. So the moment of this part of the 840 Newton force about point O is ROB cross minus 840 Newton J, and ROB is 1 meter I. I cross J, then I cross J is K, right? I cross J is K, then the result is negative, because from here, negative 840 Newton meter K. So remember here, K. Okay, so this is still easy for the moment about point O due to the 840 Newton external force. The moment of TAC about O, we can calculate ROA cross TAC, and ROA is 0.6 meter I. Okay, cross, we express TAC in terms of its ijk components as have been obtained earlier. So here what we obtain. So I cross I is 0, okay, because it is sine 0° is 0. So we only calculate I cross the j component here and I cross the k component here, okay. So 0.6 cross multiplied by 0.636 TAC Newton J, I cross J is the value equals K. This is K. So here, this component. And I cross K equal to, so using the right hand formula, yeah, right hand rule of thumb, I cross K will be equal to minus J, right? I cross K equals to minus J, like this, to the towards the negative y-axis. That's why it is minus J. 0.6 meter times 0.545 TAC Newton. So from here we obtain negative, this part, negative 0.327 TACJ plus 0.3817 TACK. So the TAC is still unknown. Moment about O from the TAD due to TAD force is similarly can be calculated using similar procedure. 0.6 meter I cross, we express TAD in terms of its IJK component, but then I cross I equals to 0, so we only calculate I cross the J component of the TAD and I cross the K component of TAD. So from here, we obtain I cross J is K here. Then I cross K equals to negative J, but since this is negative, then it becomes positive, right? So we obtain 0.257 TADJ plus 0.1716 TADK. Then using this formula, we sigma moment about point O should be 0. So this one, and each one has J and K component. This one also has the moment about point O due to the 840 Newton only has K component. So the J component will be this part, yeah, minus 0.327 TAC plus 0.257 TAD equal to 0. The K component is this one. This is from the moment due to the vertically downward external force. And from this two, there are two unknowns, TAC and TAD, and there are two equations. But from here, we can obtain both TAD and TAC. Having known this, then we can insert this into the previous equation. Sigma F equals 0, sigma Fx equals 0, sigma Fy equals 0, sigma Fz equals 0. Now we know the TAC and TAD. So from here, we can calculate OX, we can calculate OY, we can calculate OZ. Okay, although this is not yet calculated here. Okay, so this is, the time is up anyway. So this is the exercise which you can try maybe at home. So you have similarly wrote OA. It has a ball and socket joint at O. So how many reaction forces or moment there are there? 1, 2, 3, 4.
4, 5 ya.
Huh?
1, 2,
Jerry?
3,
Momen kan 3,
4,
Pak.
5.
There are no reaction moment there. Okay, because it can still
Reaction momennya.
because it can still rotate, right?
Yeah, rotate at the Z.
Disregarding first the rope, yeah. So it can still rotate about x-axis.
Oh,
It can still rotate about the y, because this is ball and socket. So remember joystick. Have you ever not seen joystick in your life
Pernah, Pak.
playing game? Belum pernah.
Pernah, Pak.
You have, right? So in joystick, you can rotate it in any direction, but you cannot translationally slide it in any axis, right? But you can still rotate the joystick like this, yeah. This, you can rotate the joystick. Rotate means like this and like this, and also like this in the But you cannot slide in. This is not possible. This is not possible because the point is fixed in that socket. So it has only 3 reaction forces, right?
Yeah.
OX, OY, and OZ. Okay, so this one OZ, this one OX, and this one OY reaction forces. So this road OA of negligible mass, so mass is neglected, supported by cables at AB and AC, and loaded with forces 500 Newton. So 500 Newton here is in the XZ axis, 500 Newton. So it does not have any Y component. And 750 Newton at and this one is drawn at the YZ axis. So it does not, this one does not have any X component, no I component. If the rod is supported by a ball and socket joint at O, determine the tension in cables AB and AC. So in this cable and in this cable, the tension. So TAB, here TAC. And the components of the reaction at O. So this one, OX and OY and OZ. Okay, so we have, the question is five unknown TAC. Well, XYZ, of which IJ and K component, of course. Okay, so maybe this can be, since time is up now, we can do this as a homework. So later I will put it in the classroom. Okay, that will be all for today. Thank you very much for your attention, and